Okay, that starts the recording, and my apologies to those of you who will only be watching this via recording here, because I had forgotten to start this up, so you've missed the first 5 minutes or so of this. Maybe I can do something to make that up a little bit later. Okay, in the meantime, let's move on. Oh, pointing to the wrong thing. There we go. Okay, am I on the right page? Yes. Okay, well, let's get into the nuts and bolts a little bit more here. What I'm going to do is do a little demo of WindBugs, and for our case, I'm just going to use a very simple model. It's just going to be a very simple linear regression as the thing I'll use to demonstrate working with WindBugs. It's going to be, again, just a simple linear model. I'm going to use weakly informative prior distributions for both the slope and the intercept. Here's a description of the model, and I've written it using what I would term the conventions used in the statistical literature. And one reason for doing that, besides the fact that that's the way I often write models, is that's also very consistent with the notation we're going to be using when we actually put the models into WindBugs. So, for example, well, first of all, let me orient you towards the symbols here. So we're going to use y for the dependent variable and x for the independent variable. And in fact, we'll just point to the data. The data is down here. I've written it in, using R convention. So our x values here are just simply an integer sequence going from 1 to 10. And then our observations, the y's, you can see listed here. And you can see that on average they're increasing as the x values increase. So that's the data we're going to work with. So the way we're going to describe that data then is it's actually going to be described as a straight line, but with some residual variation, and in particular just normally distributed residual variation. And so that's what's described by the first equation here. So we're just saying then the yi's are distributed normal with some mean yi hat and some variance sigma squared. And we'll use this little squiggle here to represent is distributed as. And then that mean in here, the yi hat, is described in terms of a straight line with an intercept a and a slope b. So that's our core model. So that is our likelihood right there. And then we have our prior distribution, which consists of 3 independent distributions for each of our parameters. We have our A and B. I've both put weakly informative priors. In this case, just set the priors as normal centered at 0 with a variance of 10,000, or in other words a standard deviation of 100, and I did the same for both. And then for our residual standard deviation, I used a uniform from 0 to 10,000. And you can see from the scale of the values that would certainly be a pretty weakly informative value on that. So it's just fairly flat over a very wide range. The other thing I've done here is shown a graphic version of the same model. And actually what you're looking at is the very kind of representation that you get if you use the GUI model specification tool within BUGS. This particular style of graphic is a particular way of showing something called a directed acyclic graph, and the underlying theory behind the compiler within BUGS, and the thing that actually goes from the model specification language you use to the machine code that it actually needs to run this, is based very strongly on the theory of directed acyclic graphs. So that's not something that's critical for you to know, but it's just a piece of information that that contributed to the way in which it was developed. But you can see all the elements here. You've got your observations, which are derived from both from the mean as well as well, it's and as well as the standard deviation, our sigma over here. We'll see when we write out the bugs code that bugs has one little quirk, and that it parameterizes the normal distributions not in terms of standard deviation or variance, but in terms of precision, which is the reciprocal of the variance, and that's what they're showing here. This tau represents that precision. So that goes. So those are the two parameters that determine our yi. So that's really our key part of the likelihood, and then we have our two parameters in here, up here, for the that contribute it to yi hat, and that's our a and our b. And then you can see this is looping over all the data points here in this bit that looks like sort of a stack of pages is what BUGS uses to represent multiple observations in here. But the key thing that I want you to get across is sort of thinking this way in terms of specifying the model, and to see how that ties back to our data that we have specified here. So right now that's just specifying the model. There's, other than the graph I just showed here, nothing here is bugs oriented in particular. We're just specifying a model with prior distributions for the parameters, because we're going to do this in Bayesian terms. Okay, so there's our model that we're going to be working with. The things that we're going to be going through will be, okay, now that's the model I want to do. How do I use the BUGS model specification language to actually specify that? How do I enter the data and initial estimates that I have here? How do I generate my MC samples? And the one premise I haven't really given you here is the whole notion here behind MC samples, or in general behind what could be termed posterior sampling, is instead of getting, say, like point estimates and some measure of uncertainty, or getting maybe an actual analytic description of the posterior distribution, what we're going to get is we're actually going to get samples from that posterior distribution. And so you get so the idea is you have to get enough samples to actually characterize that distribution. In simplest terms, you can think of this as essentially constructing a histogram that describes the posterior density for your various model parameters and for your predictions. And that's really what's going on here. And MCMC, or Markov Chain Monte Carlo simulation, is a particular strategy for doing that kind of posterior simulation. So that's what we're going to be doing. So we're going to generate those. There are some convergence issues that we'll talk about again more as we move into the theory, but I can at least give you some loose idea just kind of as we go through the mechanics. So we'll talk about assessing convergence, and we get such cute terms as the fuzzy caterpillar criteria for convergence, and the notion of actually running multiple chains to see if they where you start with different initial estimates, so you can see whether they converge to the same place. And then finally a little bit about how we analyze and interpret the results that we get from MCMC simulation. A little bit about the BUGS model specification language. Some aspects are likely to feel unfamiliar to most of you because it's not a procedural language like Fortran or C, or or even the the sort of pseudo Fortran that NMTran uses. Those are all languages that could be called procedural languages in there, and they have, how do I say this, the calculations that are done as a result of a program created with a procedural language proceed in exactly the same order as you program them. Where in our case with BUGS, it's not a procedural language, and that changes a few things. Well, one, the model specification that we're going to put in is actually has a notation very similar to the statistical literature conventions. It does not explicitly describe a sequence of calculations. In particular, the calculations don't occur in the same order as the statements that you specify. So you in a sense, that usually doesn't mean you have to take special care because of it. It probably means you can be a little bit sloppier, but every so often it can be it can do something surprising to you. Let's see what else. Some notation or some terminology that you'll see when you actually look at the help document and so on. You'll see WinBugs. The WinBugs help will refer to stochastic nodes and logical nodes. Well, those are nothing more than, well, in this case, the stochastic nodes are nothing more than probability distributions. Logical nodes would be deterministic functions. So it makes a distinction, and we'll see that distinction more clearly when you see the notation. One nice thing about bugs is it's very flexible with respect to the stochastic structure of a model. So those of you used to using non-mem, you're aware that you're pretty much restricted to 2 levels of random variation. There's some tricks where you can sort of do a third, but it is a trick, and there's some rigidity to that trick. Whereas in bugs, you can have an arbitrary number of those. Plus, you can actually have 2 models that have very different stochastic structures, all put within the same model, which you may want to do sometimes if those submodels share certain parameters, and that's very easy to do in bugs, where it can be anywhere from difficult to impossible in non-mem. So that's a strength of it. A weakness is the lack of control structures. It doesn't have true for loops or while loops, things like that within it. It also doesn't even have a true if-then-else construct within it. As a result, the other aspect that had to do with statement order is it means you don't have a lot of control over the order of calculations that are done. And the lack of control over those things can make specification of complex deterministic functions difficult. So now there actually is a workaround for that, but it's a workaround that requires some additional learning. So it kind of falls under the heading of an advanced topic in this case. Okay, let's orient you to some of these here then when we start talking about this in the context of actually writing a bugs model. And what I've got here is sort of an annotated version of the an annotated version of the WinBugs model that you'd use for that nonlinear regression that linear regression we're talking about. In fact, right here, that linear regression model is repeated. So we've got our thing again where yi is distributed normal with some mean yi hat variance sigma squared. The yi hat is just a straight line relative to x, and then we have our priors. So that's the statistical notation. How do we translate that into a bugs model? Okay, first of all bugs models are enclosed within a model block. So you have the word model and then an open brace here, and in the end of the model there's a brace to close it out. Then we've got various things going on inside. Let me just get some out of the way here. Comments, as I point out here, begin with a hash mark. So that's there. In fact, that's among many things that are going to be sort of R-like in here. So you can see we've got a comment here. Where else here? We got a few others here. Another one here, here, and here. So we got a few comments inside here and there. Now, how do we actually specify the? Actually, why don't I start with the priors here, because they're just simply inside the model block. Again, the order of statements is largely irrelevant. So I could specify the priors either at the end, which is what I did here, or at the beginning. To be consistent with the notation I wrote to the left here, I went ahead and put it at the end, but I didn't have to. A lot of people prefer to put it at the beginning. And so you can see now Notice that my three priors, as I specify them over here, are all describing distributions. I say A is distributed as normal, 0, variance 10,000. Well, in Bugs parlance, that would be a stochastic node. Stochastic nodes all use a squiggle like this for the operator, and so here is the equivalent statement in WinBugs right here. So I say A squiggle. The name of the normal distribution is dnorm inside of Bugs. And normal distributions in Bugs are parameterized in terms of the mean and the precision. And by the way, that's common error. I still do it myself, where I'll forget that and proceed to put in either a variance or a standard deviation, thinking I'm working in R or something. It has to be a precision. So again, the precision is the reciprocal of a variance. So if I want my variance to be 10,000, I take the reciprocal of that, and I'm going to get 10 to the minus 4, which is what I've got right here. Then I have the same thing for B. So I got B squiggle dnorm 0, and then again the 10 to the minus 4. Now my sigma, my standard deviation here, is going to be uniform, 0 to 10,000. So I've got sigma squiggle, and the name of the distribution in Bugs is just DUNIF for the uniform distribution, and that goes from 0 to 10,000. Now eventually what I'm going to need, well actually let's just leave it at that. So that's my prior distributions right there. Now I've got to deal with my observations here. I've got to specify my likelihood for all my observations. Let me step back to the data. Let's go all the way back because I didn't repeat that. Okay, so here's my data that I'm going to be putting in. I'm going to have the x's here. Notice there's 10 values. The y's, if you count them up, you'll see there's also 10 values of those. So I know I've got 10 observations that are in here, and they're going to be named y and x. And in here, I'm going to subscript them by an I. Now I actually have to write out a block here which looks like a loop. In fact, I will usually just call it a loop, where I'm going to say for I in 1 to 10. So the colon here then just means an integer sequence that goes from the beginning to the end here. So it goes from 1 up to 10, 10 being my number of data points that I've got. So I'm going to be looping then over that data. So it's basically going to step over all my observations from y1 to y10, and for each one of those I say it's going to be distributed normal, using my dnorm again with some mean that I called y mean, also subscripted by, I actually didn't even mention, notice the subscript syntax here. You use the square brackets with the subscript inside, and then that subscript is then the thing I specified here. I happen to use I. You can call it whatever you want. It could be J, K, or anything. It doesn't care. In fact, it can be a whole name. It doesn't have to be just a single letter like that. So I'm saying, but I used I. So my yi is going to be normal with some mean y mean I and a precision tau. Now notice I just said a precision tau. Well, where'd that come from? I didn't specify my variability in terms of a tau. I specified it in terms of a sigma, which represented a standard deviation. Well, to deal with that down here, I had to do a little calculation here where I took my sigma, my standard deviation, and calculated a precision, which is nothing more than 1 over sigma squared. So then that's what I've written here, is just 1 over sigma times sigma, and assign that to the name tau. And this is where I first introduce you to that we call the so-called logical nodes, which again are nothing more than deterministic functions, and that's what we've got right here. And notice that the assignment operator here is not a squiggle anymore, it's a left-hand arrow that you make using a less than symbol and a dash, which is actually an R convention again for that. So that's one of our so-called logical nodes in here. And so that's where the tau came from. But then how do I get my y mean? Well, recall y mean is now I've got to calculate that using this relationship here, my line, and that's happening right here. So I've just got my y mean I then equals a plus b times xi. Notice again I'm using that left-hand arrow here to deal with that assignment. Let's see here. What am I missing in here? So, well, actually, by the way, that's kind of the core of the model. I've actually got enough there to estimate my parameters once I combine it with the data and so on. But that's actually the core of the model. The other thing I've included in here is one more statement right here. See where it says y pred I is distributed normal, y mean I, and tau. Notice the right hand side of this is identical to my statement up here for yi. And so the question is, why would I do the same thing twice? And the answer is you're actually not doing the same thing twice. There's an important distinction here. This first line where I have the yi on the left hand side is specifying the likelihood function. And the reason why we can call that the likelihood function is because this yi here is actually a fixed set of values that are going to be passed via the data set. So in other words, the yi's are data. They are actual, they have hard numbers that are going to be pre-specified when you do the analysis. The things which are your unknowns really is your y mean and tau. Whereas in this statement, y pred is going to be an unspecified quantity that is being simulated from that normal distribution using the values of y mean and tau that have been estimated via the fitting process. So really, if you like, another way of I guess another metaphor for thinking about this is this statement up here. Our likelihood is the statement required for fitting. The statement here where I have y pred on the left, which is not included in the data set, is a simulation process. But you can do them all at once in one go while you're doing the fitting, as opposed to doing the fitting first and then doing the simulation as a second step. So that's something that we'll commonly be doing as we're working through our models. So we've actually just specified then a BUGS language model here. Let's see, what else do I want to tell you before we actually fire up the program and actually work with it. Actually, let me take a quick breath and see if anybody's had any questions here about what we've covered so far. Gives me a good chance to swallow a mouthful of water while I'm at it. Let's see, nothing's popping up yet. If you've got one, obviously feel free to go ahead and enter questions as we go along. Let me go ahead to the other side of this. We've only specified the model. We also need to specify data and a set of initial estimates in here. This is an iterative process that where an initial estimate is required, much in the same way it is in an optimization strategy like maximum likelihood. First of all, the data format. The format is very much like an R list. That's essentially what it is. It's a list of scalars, vectors, or matrices. Well, scalars, vectors, matrices, or arrays. WinBugs only knows numbers. It does not understand character strings. And here, can't do that. One little quirk that's a little different from R is when it comes to matrices and arrays. With R uses what is called column major entry. So if you think about the way matrices are stored in the computer when you write them in R, is they're stored where in R where the let's say it would be the row number which is moving fastest. in there. So it stores it by column, if you like. So you first of all get all of the first column, and then below that gets placed the next column, and so on. WinBugs does just the reverse. It's the rows which are stored in adjacent. You know, the rows. A row is a set of row values are adjacent to each other in the computer. And for some calculations, it's important to know that. For the particular case we're working with, we've got a fairly simple data set. It's just a list of 2 vectors. So the overall data structure is this. It's a list. And that list contains 2 vectors, one that we're calling X, the other we're calling Y in here. And notice I've used the usual C construct here to combine a set of numbers into a vector. So that's what we'll be working with there. And then initial estimates are done in essentially the same way. You specify a list structure. In our case, the only things we really need to provide initial estimates for are going to be our intercept, slope, and our standard deviation. It's as if we go back to our model, it's essentially the same things that show up on the left-hand side of any stochastic nodes where we've specified the prior distributions. Those are the key ones in there. You can specify initial estimates for pretty much anything that appears on the left-hand side of a squiggle, unless the left-hand side is also data already. So for example, we could put initial estimates for the Y preds. It turns out in this case that's not particularly useful. It doesn't hurt you, but it's a waste of time. The only ones where it's important are really the A, B, and sigma in this case. Okay, so we're going to specify those, and I won't go through this list here. You've got that in front of you if you wanted. The things that I'd like to demonstrate here, you can call me on it if I seem to be forgetting any as we go along. Okay, so I've kind of given the elements here. Let's actually go there and start doing something with bugs. Okay, let me go into Microsoft World here. Okay, now we've sent all of you. Well, don't know if all of you have received them yet, but we've sent USB drives to all of you, or at least that was the intention. And that USB drive should contain contents that look like what I've got in front of me here. Hopefully this isn't way too tiny for you to see on your own screens here, but I've actually got the equivalent USB drive stuck in my computer. It happens to have been assigned to drive E here, but it could be anything. And if you go in there, you'll see 2 different directories here, one called MI250 and another one that's called program files. And then you'll see these three files here, all ending with the CMD extension. Those 3 are nothing more than sort of they're just kind of special shortcuts that act like any other shortcut in Windows. The only thing that's special about them is they've got a little bit of code in there that makes sure it calls the programs that are inside this program files directory, regardless of what drive letter your USB drive gets assigned to. For some reason that doesn't fly for you, please let me know, but that should be the way they'll work. The one we're going to want to look at today is going to be WinBugs, and in fact let me go ahead and open up some of the directories here. So if I go down into the program files directory here, you'll see there's actually 3 programs in here. There's something called Black Box WinBugs, there's R, and there's WinBugs itself. We'll focus today on WinBugs, but there's a couple other things in there. In particular, there are you know, there's R in there, which we won't use today, but we'll use down the road. And then this black box WinBugs is actually WinBugs augmented with both our Bugs model library as well as a compiler that lets you build some of your own code. Okay, so let's move on to WinBugs here. Let me go back up to the top here. Let's fire up WinBugs. I just double click on WinBugs, the WinBugs 14.cmd, and we've opened it up in here. So we've got basically a blank slate to start with. So let's go ahead and work with it. What I'm going to do is specify essentially that same model we had before, or that I just described. I've actually got, let me go into our MI250 directory in here, and if you go inside there, there's a directory called linear, and if you want, you can go right to, where'd it go here, it's linear1.odc. If you bring that up, that's actually got the very code that I just showed you in here. So let's sort of reinforce what we were just talking about. So when you write the model, the key thing here is everything has to be in between this model with an open brace and a closed brace, and the entire model is in between. Notice again that any comments inside that model, you have to put a hash mark in front of them. Notice I've also written the word model up here, but it's outside the context of the model itself. And once I'm outside the context of that, anything I write outside of it is also, you can also think of as just being comments. So it's just annotation up here. So this is actually, this word model on top is not really, oops, just did something there, is not part of the WinBugs model itself. So just so we can see again, we've got our likelihood specified in terms of our, you know, yi, which is normally distributed. We specify we calculate the mean from our straight line, and we specify the priors again. So it's all identical to what I was just showing you. We've got our additional line here to do with predictions. So we've got again the same model. If we scroll down a bit here, I've specified the data. Again, this line up here is where it says data there is just notation. It's not a required part of the model. The only thing required here is where I've put the data inside of a list. So again, it's just repeated what I showed you on the slides. And then we have a set of initial estimates in here. So let's actually do an example running it this way. Now the process of running this is we have to first go to the menu item called Model. You open that, and then you select Specification. And then I go ahead and highlight the word Model. And if we come down here, notice that where it says check model is the only thing which isn't grayed out. I just go ahead and click on that, and it tells us, by the way, I should mention the way Bugs communicates with you is a bit terse. It's this one little gray line at the bottom. And notice here it says model is syntactically correct. Let's see, I just noticed I had a comment that got buried in the scroll line here. Can I blow something up here? Can I blow up the window? I'm wondering when that comment came here. It's difficult I haven't figured out how to blow up the things that are actually in Windows itself, but when I'm inside Bugs, I can enlarge certain things, like you can see this. So I'm not sure if I have a way of blowing up you know, things like the window up here. Maybe I could somewhere along the line, maybe I'll try changing the maybe if I change the resolution, that might do it. Anyway, I'll work on that later, maybe for a subsequent session. Okay, oops, that's not what I wanted to do. Okay, so sorry. So I go ahead and highlight the word model, and I go to, oh, I already did that. Okay, and it says, sorry, I'm getting myself distracted. So I did that. I hit check model, and it says model is syntactically correct. Now, suppose the model had not been syntactically correct, then, you know, let's see what, I'll do something to it here that'll mess it up here. Well, here, this will mess me up here. I'll misspell here. I'll say why men instead of why mean here. That should find something. Let's see. And no, it says that one's okay. That's not a that's a logic error. That one's not a syntax error. Let me find one that's definitely a syntax error. Okay, let me do something like put the wrong, wrong operator here. I don't know. I'll put I'll just put a less than here. And if I do that, I think that'll qualify as a syntax error. And it says expecting left pointing arrow, and if I click on the upper bars so that I don't mess up where the cursor is, wherever the cursor landed, and you can see it blinking right here, is where it thinks the error is. It's close to that anyway. It had to be here. Now it expected a left-hand arrow. Actually, what I didn't want that, I want a squiggle. So I'll put that back. Let me go ahead and go check model again, and it says it's syntactically correct. Next thing it expects me to do is load the data. And to do that, I just go down and highlight the word list on my data list here. I hit load data and hit compile, and it says model compiled. So in that case, everything's okay. If there was some disconnect between the data set and the model, it would have given me an error and identified some problem on that order. The next thing it wants me to do is load the initial estimates. This, it says load inits. And here I'm just going to load in this first initial estimate set. Again, I just highlight the word list and hit load inits. And it says this chain contains uninitialized variables. That's actually not a bad thing in this case. I knew that because I didn't put I did not initialize the ypred values, so that's okay. But it didn't identify any other kind of error, so that's okay. But I do have to push this gen inits button here to generate initial estimates for any remaining random variables. So I do that, and it says initial values generated, model initialized, which is a good thing. That's where we wanted it to go. Okay, so let's go ahead and see what we do from there. Well, at that point, I've actually done everything I need in order to prepare this to do an MCMC simulation. And if I go to model again and pick update, it opens this so-called update tool where I can tell it how many updates I want, which is what's up here where it says updates. This refresh here tells it after how many updates do I refresh the screen, basically. And then there's this thing for thinning, and that has to do with of the updates it does, how many of them does it keep. So if it's a 1, it means it keeps everything. If you say 10, it's only going to keep every 10th value, for example. And then when it runs where it says iteration here, you'll actually see that incrementing as it moves forward. Now, I could actually go ahead and set this and update now. There's one problem. It doesn't save, unless you tell it what you want to save, it doesn't save anything except essentially the last value. So if you actually want to save something, we have to go to the inference menu, select the first item here, which is samples, and then you tell it what you want to save. So we probably want the things like our slope intercept and our sigma here, our standard deviation. So let's do that. I say A for that, and then start set becomes available, so I set it. I do B and then set that, sigma, and set that. And we'd probably like to see the predictions too, which are these ypred values. So let's go ahead and put those in too. So we'll set that. And so now we were actually going to be able to save some things as we go. Let me go ahead and run this now. I'm going to say update. And notice that didn't take hardly any time at all. I just did 1,000 of them. Though for this particular model, you probably don't need more than that to get tolerable precision. So we've run it there. Maybe we want to look at some of those results. So let's go ahead and come back to our sample monitor tool. I can either look at each parameter individually. In fact, if I click on this pull down, notice that it tells you what you've monitored. So I've got A, B, sigma, and ypred. I could either select them, or I could use a wildcard, namely an asterisk, in which it'll give me results for all of them. And now one of the things I'm almost always going to want to do is check for convergence issues by looking at history plots. So I'll do that. And now I look at the history plots here and scroll down, and the good thing is these are all looking pretty good here. I actually gave it an initial estimate that was pretty close to the true value here, so so everything looks pretty hunky-dory even from the beginning. We'll talk more about this next time, but generally with MC methods you want to throw out a certain fraction of the values at the beginning in what we commonly term a burn-in phase. And for this particular model and with that particular initial estimates, I probably don't even need to do that. But if I did, let's say I wanted to throw out the first 100, I could, where it has BEG here, that would be the beginning value to use. I could say specify 101, which says, okay, do any subsequent analyses using iteration 101 up to, well, either the number that's here or the maximum. Of course, in this case, it'd be the maximum, which is 1,000. So if I did the history again, I'd get essentially the same thing, but now I only see 900 values in the plot. I can get representations of the posterior densities for each one of the parameters in here. I can get some statistics out where for all of the various things I sampled, I get a posterior mean, a standard deviation. This MC error is an estimate of the standard error of that posterior mean. I get some quantiles here. I've got a 2.5 and 97.5 percentile that I can use to describe my 95% credible interval. I get a posterior median, and that's about it, other than reiterating what samples that you've gotten back in here. Actually, I noticed that this, for the calculation here, it threw out the first 500. The reason for that is it's probably used an algorithm that does some adaptation. It adjusts some parameters in the algorithm for the first 500 values, so by default it throws away the first 500. So even though I said 101, it ignored me and actually used the default, which is that 501. What else here? So other pieces we want to look at. Okay, the CodeA button here. Right now, all these numbers are still inside bugs. But what if I want to save them? What if I want either save them to a file? What if I want to operate on these in a different program? The trick there is to use the CodeA button, which I'll push here. And notice that now just created two it created two new windows here. One called CodeA index, the other called CodeA. And this says it's CodeA for chain 1 because I only did one chain. And what this CodeA for chain 1 contains is, there's two columns. The first column is the iteration number, and the second column are the MC samples. But when you just look at this in this file, you don't know for which parameter those are. The way you tell that is by going to CodeA index, which here is telling me that Okay, parameter A is contained in rows 1 to 900 of that file. B is contained in 901 to 1800 in that file, and so on. So this is kind of your index to what's contained in that. And then you can use that information when you read it into something like R. In fact, that's basically what R to WinBugs will be doing for us. There's a few other buttons we'll talk about later when we talk about other convergence diagnostics and so on. We're actually going to have to cut out pretty much here, I see. I'm going to show you one more thing and then we'll close it out for the day. What I haven't showed you is anything to say, well, how well did this thing even fit? Because none of the diagnostics I've given you so far would be useful for that. Let me go to back to the inference menu to compare. So it's inference, compare, we open that up. And here if I tell it, okay, I want to look at YPRED, which I put under node, and I want to look at it as a function of x, my independent variable, and I'd like to overlay on it the observed values, y, so I put those under other, and then I click on model fit. By default it gives you this teeny tiny graph here, but we can do something about that. Enlarge it a bit. Okay, and what you get back here then is a picture where you've got the dots here represent the observed data. You get the posterior, and I forget whether default is a mean or a median here in the red, and then you get the 95% credible intervals, point-wise credible intervals shown here too, so that you can get a nice representation of the fit. Although in the case of doing this inside Bugs itself, you can only really do that effectively for pretty simple models like this one. But you can get some idea of at least what kind of diagnostics you can do just within the Bugs GUI itself by doing that. Now there's actually a few other things I'd probably like to touch on, but maybe what we'll do is I'll either hit on those at the beginning of the next lecture or possibly during the next lab session here, but I've definitely run out of time with you so far, so why don't we cut it here. I'll be talking to you again next Tuesday, and as I say, we'll probably follow up with a little bit more of this on that, but we'll definitely be talking more about what some of the algorithms are that are under the hood we're looking at. In the meantime, I do encourage you to go ahead and plug in your USB drive and attempt some of the things that we were doing just now with Bugs, just to get some idea. One of the things I haven't shown you that I'll quickly point out is if you open up the user manual in here, particularly scroll down, and there's a couple things to look at. Certainly look at the introduction, look at the model specification section, and it would be worth walking through the tutorial that they have in here. Those would be the 3 items in the table of contents I'd encourage you to look at in here. The other thing that's worth exploring is if you open it up, you'll see there's 2 volumes of examples here, example volume 1 and 2. I'll just quickly open these up. You'll see there's a list of several examples. When you open one of those up, it sort of describes the example, gives you a graphical representation of the model. It shows you the Bugs model in text mode, data and everything's in there, and you can actually run the models right from within these files to get some experience working with it. So those are definitely worthwhile, and I'd encourage you to take a look at that. At least before our next lab session. Okay, I'll close it out here and look forward to seeing you again on Tuesday. Bye for now.